We're doing the questions at the end of chapter 2, page 85, 86, 87. Get ready to do them in about 5 minutes. I'm taking attendance right now. One more time. Questions at the end of chapter 2, page 85, 86, 87. We're going to do them in about 4 or 5 minutes. Good, Joe Lopez. I'm taking attendance right now.
Good afternoon, Professor.
Whoever said that, good afternoon. Questions at the end of chapter 2, page 84, 85, 86, 87. We're going to start them in about 2 or 3 minutes. This is tedious, taking attendance, but I'm doing it. Who just came in? Oh my God. Okay. Okay, I think we're getting close to a quorum. We're going to be lecturing on chapter 3, starting in a few minutes. And I'm going to keep my eye on the attendance thing, page 85 and 86. So as usual, I'll do the first question, and then I'd like you to answer. You can either unmute or you can send me a chat, and we'll go through these for the next 5 or 10 minutes. Okay? Page 85, which is a limitation of early networks. Now, this is in today's lecture, so I'm not worried about it. The answer to number 1 is A and C, but I'm not worried about it here. We're now on page 86. Which is true of a repeater? Hint, hint, hint. Some of these questions will be on my next test, which is coming up in about 2 weeks. Rosario says the answer is C. So here it is, which is true of a repeater. What does a repeater do? It receives the signals and strengthens them. That's all it does. Okay, it doesn't receive frames, and it doesn't send a packet, and it doesn't have anything to do with burned-in addresses. It just strengthens the signal. 2 is C. That's the answer. Number 3, which is true of a hub? And it's all that applies, so there's more than one. Rosario, you're right, but I want somebody else to answer. Okay? Right. So the answer is it transmits the read generated to all the ports, that's B, and it has 4 or more ports, that's C. Okay? So the answer to 86 is B and C. Number 4, this exact question is on my next test. Well, phrased differently. What's the unit of measurement by which a hub's bandwidth is measured? So is it A, B, C, or D?
Bits per second.
Bits per second is correct. 4 is B. Know that for my test. Number 5, which describes how what does a hub do? 5, A, B, C, or D, and Y? Okay. I think, yeah, you're right. Somebody else was wrong. A hub uses C bandwidth sharing, and that's a bad thing. One more time. A hub uses C bandwidth sharing, and that's a very bad thing. Why is it bad? It slows you down. A hub uses bandwidth sharing, and that's a bad thing. Trying to see who I missed. I think I have everybody. Okay. Number 6. 6 is silly. Indicator light. 6 is B, C, and D, and I don't care about the answer. Number 7, muy importante. A switch. Which of those does a switch use and why? Yes, you're all right. I see the same people answering, but you're all right. A switch uses dedicated bandwidth A, and a dedicated bandwidth in a switch is a good thing. So a hub uses bandwidth sharing, and that's a bad thing. A switch uses dedicated bandwidth, and that's a good thing. Why is it a good thing? Because it speeds you up. Okay. We're not going to do all these, but let's go to 87, top of the page. This exact question could be on my upcoming test. Page 87, top of the page. You want to create the switching table. To create the switching table, do you use A, B, C, or D, and Y? Create the switching table A, B, C, or D, and Y. Okay, most of you are getting it right. It is D, the source MAC address. So let's remember, we forward the frames based on the destination MAC address, but we generate the switching table based on the source MAC address. By the way, I expect big things of this class. People answering seem to understand. Okay, number 9. That's coming later on. Number 9 is C. I don't care about it. Now, number 10 is neat. It's one of my favorite questions, even though we didn't really cover it. Which of those would allow a switch to go 200 million bits per second when the switch is only rated for 100 million bits per second? So the switch is rated for 100 million bits per second. Which of those things would trick you into allowing 200 million bits per second? I'm not going to ask why because you're all answering through chat, but I think you understand why. Yes, and the answer is full duplex, and here's why. I'm sending to you at 100 million bits. If you're also sending back to me at 100 million bits at the same time, our effective speed is 200. I'm sending to you at 100. You're sending back to me at 100. The effective speed is 200, even though neither one is going faster than 100. That's because of full duplex. If it was half duplex, 100, 100, 100, 100, half duplex is only 100. Full duplex, the effective speed is 100, even though the actual speed, effective speed is 200, even though the actual speed is 100. I hope you're seeing that, but it looks like from the answers of the smart people, some of you are seeing it. Okay, 11, possible test question on my next test, hint, hint. To which device is a wireless access point similar to? And the answer is it's just like a hub, not a switch, not a router, because why is it like a hub? When I send radio waves, they got to go to everybody. I can't send a radio wave only to you. How would I prevent someone else from getting it? 12 could also be on my next test, hint, hint. This is tricky. I'll let you read them yourself. What does the RTS signal do? A, B, C, or D? Pomerantz, you're right. Morales, you're right. Okay, you're all getting it right. This is very good. And the answer, of course, is C. It allows the client to notify the access points ready to send data. So here it is. Client to access point, RTC. Access point to client, that's the clear to send. So the RTS is client to the access point. The CTS is access point back to client. Okay. 13 is D, but don't just forget about it because it's silly. I'm going to stop in a minute. Okay, 14 is A and E. I don't care. 15, let's talk about that. 15, the MAC address. Is that A, B, C, or D, and Y? 15, the MAC address. Is that A, B, C, or D, and Y? And I see pausing. You have to read it, so I'm okay with that. I'm not in any rush. But I hope the smart people can get it. Okay, a lot of you are saying that the answer is B. Two 24-bit numbers, in which one, the first 24 bits is the OUI. What's the OUI in the first 24 bits? The organizational unique identifier, the one's unique to that company. Okay? What's the second 24-bit? That's the one that you're 01, you're 02, you're 03. All the others have something wrong with them. The answer to 12 is B. On my test, hint, hint, know what a MAC address is cold. I'm going to stop in a minute, but number 16. When would the NIC card allow me to take the frame in? Number 16 has two answers. When would the NIC card allow me to take the frame in? Is it A, B, C, or D? And the answer is two answers. Yes, I see the same people are doing a good idea. Yeah. So it's B, the destination MAC address is built, it matches mine, so it's obvious. And C, the destination MAC address is all binary ones. All binary ones is the broadcast address. What's wrong with A? We don't want the source MAC address to be the binary ones. We want the destination. So it is B and C. Very good. I'm going to stop in a minute, but the last one we should all know, 17, I want to capture all the frames. Is that A, B, C, or D? And no one should get that wrong. 17, which one gets all the frames in? A, no. A, no, not at all. Which one is it? Yes, you got to become what? You got to become promiscuous. If you become promiscuous, remember what I said, it's very unusual. We don't generally want to do it. It's extremely unused. But if I become promiscuous, I'm allowing all the frames in. I'm just checking for a second that I didn't miss anybody on my attendance. I'm going to stop only because I'm running out of time and I'm just getting tired. What we're going to do now, remember, the first test is coming up, and in this class, it'll be, I think, the very beginning of October. The first test is on, a guy named Sean Roche. You might want to stick later and say hello to me. I thought you were never coming to this class. So Sean Roche, when class is over, stick and talk to me because you might not know a lot of stuff. So we're about to start with chapter 3, and chapter 3 is 1/3 of the upcoming test. All right. Again, Sean Roche at the end, stay and talk to me. Everybody else can go home. And what I'm going to do now is bring up my PowerPoints. Remember, I have two full days, today and Wednesday, to finish chapter 3. And one big good news, chapter 3 isn't all that terrible. Meaning, I mean, it's I think it's easier than chapter 2 was, but we still have stuff that's in and it's on the test. All right, so let me hold on a second while I do 3 things. Share, PowerPoint. I want to turn this light off so I look better. Okay, we're bringing that up. We're bringing that down. Okay, you can still see me a little bit. Chapter 3, topologies. This is fairly easy. Will this be on my test? Yes. But remember, I tried to tell you, well, we're going to have a formal review for the test. And that will probably be next week sometime. All right, let's begin because this is 1/3 of the next test. I can never start to do this. Come on, stop it. Okay, what is topology? The lay of the land. What does that mean? The second dot, how the network is physically laid out. So how do I physically lay my network out? That is topology. How does my network physically look? How is it physically laid out? That is my topology. Okay? And forget about the bottom dot. We'll talk about that later about logical and physical. It's very important, but we're going to talk about it today in a few minutes. But I want to cover it now. The middle dot's the big one. The lay of the land. How is the network physically laid out, and how do the signals travel? Now, again, you have to know this in my test, but I'm telling you, this is not anywhere near as hard as the stuff we've done so far. Nobody should get this stuff wrong. Okay? Again, physical and logical is slightly different. I'm going to get to that in slide 14, 15, or 16, and we'll get to that today sometime. Now, remember, I have 2 days. I have today and I have Wednesday to finish this stuff. All right? Muy importante, the last dot. We would have a bus topology. We would have something called a star topology. We would have something called a ring topology, which you should have no problem with, because a ring is what? A circle. And we'd have a point-to-point. Each one of those is what we're going to cover in the next few slides, and we have to know all 4 of those for my next test. The good news is it's not that difficult. I mean, it's not that hard. Okay? But the topologies are the bus, the star, the ring, and the point-to-point. Everybody okay? Okay, the bus is a continuous length of cable. Now I'm going to come back to this slide, but let me just show you something. This thing here, this wire, that's a bus. And you see how they're daisy chained together? That wire is the bus, and they're daisy chained together. All right, so let's go back to the slide. Top dot, a continuous length of cable going from one computer to the other in a daisy chain fashion. It's the simplest and most common that we used to use but don't use anymore. One more time. The bus is the simplest and most common at one time, but it's never used today. By the way, why is it never used today? It just doesn't work well. And we're going to find out why it doesn't in the lecture in a minute. It's true we can't do any more than 30 computers, but who cares? It's true that the maximum length is 185 meters, but who cares? This is the big one. Any break brings down the entire network. And we're going to get to that in a minute, and you have to know that for my test. So the bus is the old one that's a waste of time that we never use. Here it is. Due to its limitations, the bottom. It's no longer a practical choice, and we've moved past this obsolete method. We don't use the bus anymore. Now, a few people say, okay, I got that, Professor, now you can move on. But a few genius people are going to say, Professor, could you tell me why is that not possible? Why doesn't the bus work? And yes, we're going to find that out. And hint, hint, yes, you need to know this for my first test. There's the bus. This wire here that connects them together is the bus. Now, again, I told you I've sorely missed writing on the blackboard, but I can't do much about that. This slide, muy importante. We're going to go from the bottom up. Now, let's see if I can talk to you. You can see me. If I've got a wire that goes like this, the signal goes from me to you and you to me along this wire. What happens when the signal gets to the end of the wire? Well, you would think that when the signal gets to the end of the wire, it would just fall off. In fact, oh, you geniuses, something unusual happens. When the signal gets to the end of a wire, the signal will bounce back. Signal bounce is a term used when electricity bounces back from the end of an open wire. You would think that the wire's open, the signal would just fall off the end. Instead of the wire's open, the signal hits the open end and bounces back, ricocheting bullet. So signal bounce is a bad thing. It bounces off an open end of a wire. Now, big cuidado. What can I do to stop signal bounce? The second dot from the bottom. The signal continues until it weakens or until it's absorbed. A terminator is something you put at the end of the wire that absorbs the signal instead of allowing it to bounce back. So here it is. On a bus, signal bounce is a very bad thing. How do I prevent signal bounce? I terminate the wire. Termination is a good thing. Why is termination a good thing? Because termination prevents signal bounce. Peter Piper picked a peck of pickled peppers. A hint, hint for my smart students. There would be a question on my test from this slide. Now, I assume they're dead silent. You know, for the new people who haven't been here a while, you can ask me a question by chat or you can unmute and ask me a question. But I assume the dead silence means you understand this. Let's go back a couple slides. It said here, any break in the bus brings down the entire network. Well, let me try to show you something. There's a bus. It doesn't show it, but the ends would be terminated. Now, what would happen is if I broke the middle of the bus, okay, the ends are still terminated. But if I make a break in the middle, these two ends are now not terminated. One more time. Here's the wire. Termination, termination. Here's the wire. Termination, termination. If I break in the middle, I've still got termination, termination here, but I've got no termination on these breaks. An unterminated end brings the entire network down. So a single break in the wire and the entire mother sticking network can't function. And that's the main reason why we don't use it anymore, is because of that. Any break in the bus brings down the entire network. One last time before I move on. On my test, the bottom dot. No, the signal bounce is a bad thing. No, that we prevent signal bounce with the dot above it if we terminate it. And the big cuidado is this one. This only applies to a bus. This does not apply to any other topology. I'm pausing. I think we understand it. I don't want to go too fast or too slow. I have great hopes for this class. It sounds like you people know what you're doing. Okay? So let's move on slowly.
So nowadays, they don't use that bus topology anymore, right?
Absolutely. See what it says? Once this obsolete method, you'll never see a computer. Well, I don't want to tell any anecdotes, but I'm pretty old. And when I first started teaching in a trade school, we used this topology. And in fact, the story I have to take is every morning when we come in, it wouldn't work. So I'd have to say, okay, everybody, guys and girls, get under your desks. Why? You'd have to go under your desk and look around. And then somebody say, Professor, I found the break. This wire was loose. Professor, I found the break. This BNC was loose. So when someone found the break and tightened it up, then we could work. Well, in a classroom with students, you can kind of get away with that. And you see why in an office, you don't want executives and secretaries getting down on their hands and knees trying to find out why there was a break. So this was never a very practical way to do it. Did it work? Yes. Was it a good idea? It was the best they could do at that time. So whoever asked the question, that's the answer. Again, I want to move on. Know this slide. Okay? Forget that. Okay. The star is the one we use. I'm coming back to the slide in a minute. The star topology is the one we use all the time. I'm coming back to the slide in a minute. Does everybody see why this is a star? I want to send to you. I go through the switch. I want to send to you. I go through the switch. I want to send to you. I go through the switch. It's a star. It radiates out. Now, here's the other cuidado. If this wire breaks, this poor sucker's off the network, but it doesn't affect any of these people. If this wire breaks, this poor sucker's not in the network, but these people are still okay. They can keep going. So one wire break will affect that one person, but it will not affect the entire network. Let's go back. Here's the slide. The star is the most popular. It uses a central device to connect computers. It's faster than a bus. The centralized thing is better, and it's easier to upgrade. So the star is the one we use all the time today. You go to the classrooms at Bergen, they're all star. And again, the people who want, a couple of people, this is their first day. People who were here last week and the week before, you know why a switch is better than a hub. You know what I mean? And you should be okay with that. All right, let's keep going. So the star is the one we use all the time. The bus is the one we never use. What's so great about a star? Central device. Now, that's that thing in the middle, the hub or the switch. See the first line? It says hubs and switches can include software that can collect statistics. So I can monitor the traffic with that hub and switch. And this is tricky. We can always update it. Let's read this one. When the number of workstations you need exceeds the ports, you simply upgrade it. Let me try to show you that one. Let's say this was an 8-port switch, and let's say we need 8 more ports. So we could do one of two things. We could add another 8-port switch on top. Now we'd have 16 ports. Or, here's the biggie, we could throw this the heck out and buy a 16 or 32-port switch and put it in. So we could either replace that switch with one with more ports, or we could buy another 8-port switch and add them together to get 16. That's what we mean with this one here. Number of workstations you need exceeds the number of ports. You simply replace the central device or add another central device. So the hub or the switch, the star is the best way to go. And again, all the people who were here for chapter 2 understand the difference between a hub and a switch. Okay, we all got that? Now, this slide says the same thing. I'm going to go back and forth. An extended star is a star of stars. That's a star. That's a star. That's a star. And that's a star. But we want to connect them together. So we took 4 small stars and put them together through a star of switches to get what we call an extended star. That is, we can keep expanding a star almost infinitely. So one more time. This is a star with 20 computers. There's a star with 20 computers. There's a star with 20 computers. And there's a star with 20 computers. We starred them through a switch. So now this guy can talk to this guy, but this guy can also talk to this guy. That's your extended star. And see this picture here? Well, the next slide is going to talk about it. A central device sits in the middle. Instead of attaching computers, we attach other switches. That's called a hierarchical star or an extended star. It's called a hierarchical star at the bottom, or it's called an extended star. It's still a star. It's just another variation of the star. It's a star of stars, if you want to put it that way. Okay. Now, again, you have to know all this stuff, but I think this stuff about a star, a bus, and a ring is not as difficult as stuff we did up till now. I'll be very upset if you don't know it, but unless you're not too bright, you should know it. It's pretty straightforward. And by the way, except for the people who missed my first few classes, and even trying to get the real certification, we're getting through a lot of the techno-babble for it. Just a little hint, this class gets a lot more interesting in the second half. It also gets a lot more difficult. The first half is simply concepts. Not that it's easy, but it's concepts. Know what a star is. We can all go home. I'm going to talk about this completely differently. Well, I'm skipping this because I'm going to talk about this in slide number so-and-so. I don't know which one. Now, what's the disadvantage of a physical star? There's almost none. See the top dot? Physical star is the best way to go. But there's one mother-sticking disadvantage, and that is that first line. The central device, the switch, is the single point of failure. If that thing in the middle fails, you're toast. So if the hub or switch fails, or someone kicks the power cord out, or someone spills Coca-Cola, and that thing goes down, the entire mother-sticking network is down and you're screwed. So there's no way around that but the bottom one. Have a spare online. How do you prevent the power cord from being kicked out? Don't put the switch out in the public area. Put it behind a fence. Put it in a locked cabinet. But the only disadvantage to a star is that the switch or the central device, if that fails, you are toast. You can't let that fail. It's the only disadvantage, but it's a very, very, very big one. Know that. It's pretty obvious, but know it. Right? Now, this one a lot of students have trouble with, but they shouldn't. And I missed the blackboard in this case, but let me see if I can do it. So we already covered that the bus was like this. It's going back and forth, right? And then we said you had to terminate the ends of the bus. Otherwise, you get signal bounce. Well, is there a different way to do it? Read this while I explain it to you. If I've got a bus going out this way and I don't terminate the end, I'm going to get bounced. Is there another way to do it? What if I took the two ends and brought them around? One more time. The two unterminated, and I brought them around and connected them. What am I going to have? I'm going to have a circle, but I'm not going to have a terminated end. So instead of terminating each end, the cable is brought around from the last device versus the first device to perform a circle or ring. It's another way to prevent the end from being unterminated. And now we don't have any signal bounce, and now it works. Well, does it work? Yes. Now the data keeps circling like a giant circle. Big cuidado. If you break anywhere in the ring, everybody's down. With the bus, if you break anywhere in the bus, everybody's down. With the ring, if you break anywhere in the ring, the entire network's down. But we don't terminate with a terminator with the ring. We bring it all the way around. Hint, hint, hint. You might want to know this on my upcoming test. Now, the one they keep talking about here is this stupid fiber optic one, but I'm really pushing what a ring is. Now, we'll talk about this. The data travels in a ring in one direction, and if any part of the ring breaks, we're screwed. FDDI is a special thing. It's a fiber optic ring. Big cuidado, this word here. it uses 2 fiber optic cables. So if I've got data going in one fiber optic cable and the same data going in another fiber optic cable, what happens? If this one breaks, the other one takes over. If this one breaks, the other one takes over. So if I've got 2 cables, only one breaks, the other one keeps going. So what we're having is 2 fiber optic cables for redundancy, to make sure that if one breaks, the other one keep going. That's the FDDI one, a special case. It's fiber optic, the data travels in a ring, but there's 2 rings, so if one breaks, the other one can take over. A ring is simply a giant circle. Know what a ring is for my test. Huh? This is, I don't like this, I'll tell you why. This is supposed to be a fiber optic ring. But look, it's one circle. What they're not telling you is inside this wire would be 2 fiber optic cables. And they're also not telling you something else. If the entire wire breaks, and if both fiber optic cables break, you're toast, you're down. But if only one fiber optic cable breaks, the other one takes over. But again, if both of them break, it's like a regular ring, nothing happens. Okay, I'll do this one. I don't like it, but I have to do it. Now we'll get to what I call the sexy one. Point to point is pretty obvious. One computer to another or one building to another. So point to point is one computer to another or one building to another. That's pretty obvious. The one they're introducing that's a little bit tricky is this point to multipoint. A central device communicates with 2 or more devices, it all goes through the central office. Now let me try to explain this. I'll come back to the slide. Let's try it. If I can go directly to branch office 1 or directly to branch office 2, that's point to point. But if I got to come from my computer and go through the main office to go to branch office 1, my mouse doesn't work, and I got to go through the main office to go to branch office 2. Oh, fuck you. Okay, that's point to multipoint. So let me go back one. If all communication must go through the central office to get to someplace, it's point to multipoint. If the communication goes directly to the place you want to without going through anything else, that's point to point. So point to multipoint would mean all communication has to go through an interim or central office to get to the place. That's point to multipoint. Point to point, directly to me to you. I don't like this. It's a new thing in this book, but it's a definition. For the new people, I was trying to explain that this entire course is what I call techno-babble, techno-terminology. The way to pass all my tests is simply know the terms. And we've covered a hell of a lot of them so far. A lot. And there's point to multipoint. Everything has to go through the main office first. That would make it point to multipoint. If it could go to branch office 1, 2, or 3 directly, it would have been point to point. Since it can't, that's point to multipoint. Now, the next one is super easy, but it's a point I want to make, and you might want to pay attention. And that is mesh. Well, mesh is you got to visually. Say we're in a classroom, and you all have computers, and I'm up front. With the star topology, we would all go to a hub or switch. So I go to you through the hub, you come to me through the hub, and that's the standard topology. What if we had mesh? My computer would be directly wired to you, you, and you. And your computer would all be directly wired to me, but it's worse than that. You would be wired directly to you, and you would be wired directly to you, and you would be wired directly to you. Every computer would have a direct link to the other computer. Now, that would make sure that there would never be a way you couldn't get there because there'd be so many paths. Would that be a good idea? Well, it sounds good at first glance, but if you think about it, it really wouldn't. Because if we tried to wire a classroom that way, we'd be knee-deep in wires. We'd have a wire from you to you, a wire from you to you, a wire from you to you, and by the time we're done, we'd have a couple of feet of wires on the ground. So due to multiple interfaces and cabling, we don't ever use this in wiring up classroom computers. This is never used in wiring up classroom computers. So you can just forget it, it's never used. Well, hold the phone a minute. It is used in one major time. When is it definitely used? And this is the next slide. So when would I use a mesh topology point to point? And the answer is the last one, large WANs. What do they mean by that? Here it is. Chicago has a direct connection to New York, Phoenix, and Los Angeles. New York has a direct connection to Chicago, Los Angeles, blah, blah, blah. Each city is directly connected to every other city. Now, if Los Angeles and New York want to talk normally, they're probably going to use this wire here. And that's how they'll talk. But what would happen if this wire broke? Well, now New York could go to Los Angeles this way, or it could go this way. See what I'm getting at? So there's several ways that New York could go to Los Angeles. The normal way it's going to go is in that middle wire right there. It's going to take that regular wire and go, okay? But if it can't take that regular wire and go, it's going to go through the other way. So the mesh topology is used on the internet and on the wide area network. It's just not really used for wiring up. That's mesh, point to point. Everybody's directly connected to everybody else. It's not used on a regular network because it's just too much wire. It is used here because we want the redundancy. Right? So, okay, I'm going to move on to something very sexy in a minute. It's a little bit difficult. So what I want to do is review here. What do we have on the slides 7 or 8 slides ago? We had a star, a bus, a ring, and a point-to-point or mesh. So the bus was the one that we seldom use. We never use anymore. That's the one that had the signal bounce and the termination. The star is the one we use all the time. Star is the one we like. Extended star, that's the one we use constantly. The ring is a circle, and it's another way to prevent the termination. Remember, we came around. We didn't have to terminate. And the ring works like a ring. If you break one, we're all down. And then the mesh or point-to-point is never used in a wired network because it's impractical, but it is used here. Know what a star is, know what a bus is, know what a ring is, and know what a mesh is, and know all the characteristics for my next test. Now, is this important? Yes. But I would argue it's not as difficult as all that MAC address garbage we did last week. Okay? Which you also have to know, but it's not as difficult. So I'm going to slow down for a minute or two. It's 3:49. We'll be out of here by 4:15. Remember, I have today and next time to finish this chapter. But this stuff will be on my first test. I already know the date of the first test. I can already tell you it's not next week. I think it's the week after next. So don't worry about it. But it will cover chapter 1, 2, and 3. And we're in chapter 3 now. All right, let's keep going. Now, this is a little bit tricky about the logical and physical. They introduced this twice, and I left it out. I'm going to try to do it now. Topology. How is it laid out? What's logical topology? The top dot. How does the data travel? Well, you say, Professor, I don't understand. The way it's laid out is the way the data travels. And you know what? You're almost right. Let's look at this dot here. Let's say you have a bus. What is a bus? It goes like this. How does the data travel? The data has to go like this. Why? It's a bus, and the wire is like this. There's only one way for the data travel, in a bus like that. So if a bus, a logical bus and a physical bus are the same, the data travels logically as in a bus. If it's physically wired as a bus. Logical bus, physical bus, the same, never any change. Let's do a ring. What's a ring? It's a giant circle. How's a ring shaped? Like a circle. How do you think the data is going to travel in a ring? It's going to travel around in a circle. Well, what if I don't want it to? Well, how are you going to prevent it? The damn thing's a circle. It's going to travel like in a circle. So with a physical ring, we always have a logical ring to go with it. There's never any difference. So a bus, physical and logical are the same. A ring, they're the same. But for the geniuses, there's one problem. The star. That could have variations. So let's see the next couple slides. So here is a thing that's wired like a star. Now, why is it wired like a star? I radiate out like a star. Now, I can't do the thing with my hand, but in class, I would cover this up with my hand. You don't see this thing in here. So all you see is a box. And you say, what is that? It's a star. How does the data flow logically? You say, probably a star. And you'd be right. It probably would be a star. But I'm telling you that in this particular case, the data is flowing in here back and forth as if it was a bus. Now, I know what you're going to say, the smart students. Well, Professor, how would I know that? You know what? You wouldn't. Someone would have to tell you, in this device, it flows like a bus. So in this case, what you have is a physical star, but you have a logical bus. Well, Professor, how would I know that by looking at it? You wouldn't. Someone would have to tell you that's how it flowed. There's a case where the physical and logical topology are different. But the next one is the more important one. This one isn't too important. And I'll stop and see if you have a question after the next one. This is a little bit difficult. In this case, we're wired out like a star. It comes out of the box like a star. But I'm telling you that the way the data flows, it goes back and forth, up here, back into here, up here, back into here, up here, back into here. It's flowing like a giant looping ring. It's flowing around and around like a ring. So you say, wait a minute, Professor, I look at it, it looks like a star. It is. How would I know it's not a star? You wouldn't. Someone would have to tell you that the data is flowing like a ring. By the way, give me a drum roll. This is the famous IBM token ring. This is the famous IBM token ring. Now, they keep saying logical ring like physical star. I'm going to say this backwards. It's wired physically like a star. It's a physical star. But the data is flowing logically as if it was a ring. This is the famous IBM token ring. And this is these two examples, but particularly this one, is the only time I know where the logical and physical topology are different. In a ring, logical circle, ring, circle, they're the same. With a bus, logical and physical the same. With a star, there's three choices. It could be a physical star and also flow logically like a star. So it could be a physical and logical star. It could be a star, but it could be a logical bus. Or it could be a star and it could be a logical ring. Peter Piper picked a peck of pickled peppers. Okay?
So there can be a mix of wire and non-wires.
No, probably not. I don't know theoretically, but probably not. That's not what I'm getting at here, but I'd say unlikely. Does everybody now know how logical and physical are different? This is a little bit complicated for some people. That's why I'm slowing down. I'm assuming the dead silence as I lecture means it's a pretty smart class. And from what I've been seeing from the questions at the end of the chapter, I think this is a pretty smart class. So I'm looking forward to a test, I believe, the week after next to find out if it is. Okay? But I have great plans for this class. You seem like you're all taking it seriously. All right, so let's move on. Remember, I promise you the second half is a little bit harder, but it's also more interesting. The first half is all techno-babble, techno-terminology. And doesn't we have to get through it? We have to know it, but it's not as interesting as it could be. All right, let's move on slowly. We'll be out of here by 4:15. How's that? I don't like this slide, but I'm going to do it anyway. The difference between logical and physical, and what they're saying here is this. You've got 6 people plugged in. So you've got 6 physical connections because you're plugged in, but nobody's talking. Since nobody's talking, you've got 6 physical connections, but not a single logical connection. We're all plugged in, but we're not communicating because we're drunk, we're asleep, whatever. Now, let's go over here. We now have 6 people plugged in. We got 6 physical connections, but only 2 and 5 are talking. So what we have is 6 physical connections, but depending on how you look at it, only 1 or 2 logical connections. I'd say 2, because 5 and 2 are talking to each other. So 6 physical connections and only 2 logical connections. Now let's look for a minute at this guy here. 5 and 2 are talking to each other. What's this stupid dotted line between 1 and 6? Well, what it's saying is, if 5 and 2 are talking, 1 and 6 are thinking of talking. Why can't we talk? So here's my question. If 2 and 5 are talking, can 1 and 6 talk at the same time? Well, if this was a hub, of course not. But with a switch, why not? If you and I are talking in these 2 slots, why can't you 2 talk on these 2 slots? And then why can't you 2 talk on these 2 slots? So while 2 and 5 are talking at the exact same time, 1 and 6 could talk. And to even get worse, at the exact same time, 3 and 4 could talk. See what I mean? That would be logical. So when the bottom line, when no data is being transferred, you're not logically connected. As soon as you start transferring data, then you are logically connected. You're always physically connected, but you're not logically connected until you transfer some data. I don't think this is very important, but I mean, how can I say it? I don't think it's very difficult, but I think it's easy to understand. Okay, this should be an easy slide to understand. And again, I'm assuming the dead silence is that most of you are catching all this. I want to go as far as I can, but I'll finish this next time we meet. I'm skipping this. Oh, I know how I'm going to end this. We have only a few more slides, but each one is one of those long things. I don't want to talk about this or this or this. Now, let me talk about this just for a second. Next week, we're going to go to chapter 4. And chapter 4 is an entire 2-day lecture on just wires. It's called media. And if we learn in chapter 1 and 2, the medium is the wire. So we're going to talk about fiber optic cabling in nauseating detail in chapter 4. We're going to talk about twisted pair wire in nauseating detail in chapter 4, and same with coax cable. This stuff in chapter 4 will not be on my upcoming test. This will be on the pre-Halloween test. So I told you, when you're trick-or-treating, you will have taken 2 tests from me. One is coming up the week after next. The other one's coming up Halloween week. This will be on the Halloween week test. Okay, so I'm not going to really talk about it now because we don't want to overload our feeble brains. But this one I am going to talk about. I'm going to take about 5 or 10 minutes on one slide. It says that baseband is digital signals and the broadband is analog signals. And I used to just teach it that way. Till I found the disturbing thing that a lot of students don't really understand the difference between digital and analog. So I ask a student, they'll say, well, my analog clock goes around like this and my digital watch has, numbers on it. Well, that's true. That's a digital watch, that's an analog clock. So there is a difference. But how does a digital signal and an analog signal vary? So here's my little anecdote. I'm pretty old and I grew up in the era of records. And I was a big Elvis Presley fan. So when Elvis Presley would sing, he would bump and grind and do everything. The bottom line is he generated a voice wave. And that voice wave is the actual wave of Elvis's voice singing. And you can actually plot it. When he's singing Hound Dog, there's the sing of Elvis singing Love Me Tender or Hound Dog, and it's going up and down like that. The actual voice wave of Elvis or Frank Sinatra singing, that's an analog wave. An analog wave has an infinite number of values. It goes up here, it goes down here, it goes up here, it goes like this, and it goes like this, then it goes like this, and it goes like this. So an analog is the actual voice wave. I don't know if you know it, but records, 33, 45 RPM records, are wax. And in the wax is etched the voice wave of Elvis singing. So if you put a record on a turntable and spin it, and you don't turn the amplifier on, and you listen carefully, you can hear the needle vibrating to the words of Elvis singing. So in other words, a record has an analog voice wave of Elvis or Frank Sinatra on. And that's analog. Well, you say, Professor, that's very interesting. But I listen to CDs and DVDs. How do they work? Well, CDs and DVDs have all ones and zeros. Here's a 1, here's a 0. Now, there's no 1.5, 1 3/4. On, off, 1, 0. There's nothing here, there's nothing here. It's either 1 or 0. Fully on, fully off. So now you've got a series of 1s and 0s. That series of 1s and 0s, on and off, that's digital. Okay, Professor, I got that, but how does that mimic Elvis singing? Well, it doesn't. Here's what happens. What they do is they take the sound of Elvis singing and they create a computer program. And that computer program is what's on your CD or DVD. Not Elvis's voice wave. It's the computer program of Elvis singing. Let's do it again. On a record is the actual voice wave of Elvis singing. On a CD or DVD is a computer program of Elvis singing. So I don't have my blackboard. I miss it. If I can write a 1 or a 0, high or low, that's digital. If I put a continuous voice wave, that's analog. That's important. So baseband is sending only 1s and 0s. One more time. Baseband sending only 1s and 0s, sending completely digital signal. Broadband sends an actual wave, Now, it's not a sound wave, not even a voice wave, but it's an actual analog technique of varying things. So broadband is an analog signal constantly changing. Baseband is a digital signal constantly changing in a different way. All 1, all 0s, all 1s, all 0s. Baseband, digital, broadband, analog. Know what analog is, know what digital is. One lousy slide. What did I spend? 6 to 7 minutes on it. Again, people remember my last chapter where I spent a lot of things on one slide? Know this slide. Hint, hint, know this slide for my upcoming test. Okay, I'm still watching. It's 4 o'clock. We'll be out of here by about 4:15 because I don't want to keep you too long. But we're going to finish this chapter on Wednesday. I want to introduce this, though, because I want to be able to do this at least twice. This is a little bit tricky. This is more techno-babble learning. Ethernet is what we all use. It's the most common local area network technology. Ethernet was invented in the 1970s. It's been around forever. So when you say, what are you using on your network? At home or here? You know what it is? It's all Ethernet. Ethernet's all we use. Now, that's easy. Here comes the hard part. I want a drum roll, except for the few people who showed up for the first time. Everybody in this class should have this down cold. What's the MAC address? The same mother-sticking MAC address we learned in chapter 1 and 2. What's the second dot? 48-bit binary, 12 hexadecimal digits. Nobody in this class shouldn't know that cold. The same MAC address, not a different one, the same one. The broadcast address, what does that mean? Well, remember, there is no for F, but F isn't really F. F is hexadecimal F. And hexadecimal F is what? 15. How do I put 15 in binary? 15 in binary is 8 plus 4 plus 2 plus 1. So 15 in binary is 4 binary ones. So if this is 4 binary ones, and then this is 4 binary ones, and this is 4 binary ones, what do I end up with? I end up with 48 binary ones. Well, what is 48 binary ones? The same broadcast address we just practiced in the questions at the end of the last chapter. So this is the same MAC address with the same hexadecimal with the same broadcast address. Again, drum roll. We covered the MAC address in chapter 1. We covered the MAC address in chapter 2. We're covering again in chapter 3. Hint, hint, hint. There'll be several questions on my test on the MAC address. You better know it cold. Okay, 3 chapters of MAC address. Right? It's the same one, nothing different. But here's the point that I didn't make, and they should make. When I'm sending an Ethernet frame, Ethernet uses the MAC address. So how do I get from my computer to yours on an Ethernet frame? I use your MAC address, the same MAC address we talked about. Ethernet forwards data based on the MAC address, the same MAC address we learned in chapter 1 and chapter 2. All right? Be sure to know all that OUI stuff, the first 24 bits, second 24 bits. Be sure to know all about hexadecimal. Be sure to know the MAC addresses on the NIC card, all that stuff from that slide in chapter 2. But it'll all be on my test. Now, we're going to spend a good 20 minutes, a good 5 or 10 minutes on this slide. Again, the bottom up. A frame. Well, except for the few people who missed. What's a packet? A packet has the IP address and data. How do I make a frame? I frame the packet. Now, here's where you're going to see it better than all. Let's say this is the packet. What do? I frame the packet on the front end with the to and from IP address, on the back end with the error checking. Let me do it again. I frame the packet on the front end with the to and from MAC address, and the rear end with the error checking. So I took a packet and I framed it. That's what makes a frame. So what does a frame contain? The source and destination MAC address. Now, I'm really unsympathetic. This is the 3rd time we're covering this because we covered this in chapter 1 and 2 from a slightly different angle. So now we're covering the same thing from a just slightly different angle. It's the same frame. The big cuidado that's new is the 1518 bytes. Now, here's my little lecture on that. A frame can be any size you want it to be. There's no limit to the size of a frame. However, we always use Ethernet. And if we choose to use Ethernet, then a frame can't be any bigger than 1518. So could a frame legally be bigger? Yes. Will you ever see a frame bigger than 1518? No. Why? Because we never use anything but Ethernet, and Ethernet's limited to 1518. Big cuidado. That's 1518 bytes, not 1518 ones and zeros. It's not 1,500 ones and zeros. It's 1,500 8-bit characters. Can it be smaller than that? Yes. Can it be bigger than that? No, never. What does a frame contain? A source and destination MAC address, just like we did in chapter 1 and 2. So we're doing a new lecture, but we're really using the stuff we did in the first 2 chapters to do. Okay, let's move up slowly. The middle dot. That looks like Ethernet II. Ethernet II used by TCP/IP. That's really Ethernet Roman numeral 2. So Ethernet Roman numeral 2 is a frame type. Now here's where it gets a little confusing. There are 4 different frame formats. I used to have to teach them, but I'm not going to teach them why. But even though there's 4 different frame formats, the only one you're ever going to see is this one. Ethernet Roman numeral 2 must be used by TCP/IP. We haven't gotten into TCP/IP in detail yet. Believe me, we will later on. We decided in chapter 2 that the most commonly used protocol that we're ever going to use is always going to be TCP/IP. Since that's the only protocol we're ever going to use, the only frame type we're ever going to need is Ethernet Roman numeral 2. Why is the size of a frame never bigger than 1518 bytes? Legally, it could be but the only frame we're ever going to use is an Ethernet frame. And since an Ethernet frame is limited to 1518 bytes, we'll never see a frame bigger than 1518 bytes. Peter Piper picked a peck of pickled peppers. Have we all got this stuff? Again, what did I spend? 5 or 10 minutes on one lousy slide. You've seen me do this before. Again, this stuff's a little tricky, but I think this whole chapter is a little easier than the previous one. No Ethernet Roman numeral 2 frame type, and know that the frame size can't be greater than 1518 bytes, and be sure to know the difference between a packet and a frame. Now that we did in chapter 1 and 2. That you got to know, Cole. But what did the frame contain? It contains a MAC address. Sure enough, it contains a MAC address, and they're showing it there, and they're showing it here. Right? Everybody got that? I'm watching my watch. We'll be out of here by 4:15. This one. I'm going to do both of these next week because this one is on my test, and it's very difficult. Ethernet uses a media access method called carrier sense multiple access collision detection. And when I say that, it sounds like a mouthful, but we're going to give a good lecture on it. So let's assume that we're in school together and I don't have my car. And I'm the professor and you're the student. I say, Joe or Jane, could you give me a ride home? And you say, sure, I can. So when you're pulling out on the main thing, you're pulling out the Paramus Road, I say, you know what, I'm going to hurry to get home. Hurry up and pull out and drive me home. And you say, well, look, professor, I understand you're in a hurry to get home and you're the professor, but I have to edge out into traffic. So I'm the driver. So I'm going to wait here until I see a space in the traffic. And I say to you, now, don't bother with that. That's garbage. Just pull out. You say, but if I pull out, I'm going to smash my car. So here's how this works. When you hit the enter key to send an Ethernet frame, okay, your NIC card says, yes, you told me to send, but I'm going to do something. I'm going to listen before I send. In other words, you asked me to send the frame, but I hear a lot of traffic going by. Even though you told me to send the frame, I'm going to wait until I hear a break in the traffic and then I'll send it. Why? If I send the traffic while the other traffic's going by, I'll crash and lose everything. But if I wait for a break and send, it'll get through. You tell your computer to send the frame. The computer's NIC card says, no, I'm going to send when I think there's a space. That's carrier sense. You're sensing the silence. You're listening to it. And here it is. If 2 or more stations hear the silence, then it says, okay, I'm going to send it. So even though I'm nagging at you, when you see a space in traffic, you pull out. And we're all happy, right? Well, that's the lecture, except here's the problem. Once in a great while, 2 or more stations may see a silence and they may transmit. I heard silence, I transmitted. You heard silence, you transmitted. When that happens, we're both going to collide. And what happens when we collide is you lose your frame and I lose my frame. We lose all our data. Now, we'd kind of be screwed. But what has to happen is the network card has to somehow sense the collision, know that you crashed, and then resend it. So let's try it again. CSMACCD, carrier sense. Your network interface card is going to listen before sending. What's it going to listen for? A break in the traffic. It's going to listen for something called silence. Okay. And most of the time, it's going to send properly, and that's the lecture. Once in a great while, 2 network interface cards will send at the same time. They will crash. That would be a royal screwing, except for one thing. There's a mechanism to detect that collision and tell each NIC card, you know what, sucker? That last thing you sent crashed. You're going to have to resend again. The collision detection is the ability to detect the collision and have the NIC card resend it so you don't lose that frame. And here it is. Ethernet always uses CSMACD, and CSMACD is the way Ethernet works. So for all practical purposes, Ethernet is CSMACD, and CSMACD is Ethernet. Hint, hint, hint. Now all of this for my first test. I'm going to do all of this next time because I want you to see it twice. It's difficult. See, how much time did I spend on one slide? Do I need to know the term CSMACD? Yes. Do I need to know how it's used? Yes. Do I need to know that it's a major factor in Ethernet? Yes. I'm still watching my watch, but I'm going to let you go in a minute or two. Okay. So no CSMACD, but we will do that one next week again. All devices separate collision domains. I'm going to come back to this in a minute. Yeah, here it is. So let's try it. Okay. I can't do it. I have to do it this way. Let me show you. These are connected with a hub. These are all connected with a hub. This guy can talk to this guy. This guy can talk to this guy. If somebody here talks to this guy and this guy's talking to this guy, could we have a collision? Yes, we could have a collision. We need CSMACD to prevent them. Let's go over here. This guy is talking to this guy's talking to this guy, and they're all connected with a hub. Could this guy and this guy send at the same time and collide? Yes, they could. We need collision detection. But watch carefully. If this guy wants to talk to this guy, he's going through what? Not a hub, but a switch. What does a switch do? A switch only forwards to the person you're going to send it to. Could anybody in here ever collide with anybody in here? It's not possible. Let me try it again. This guy might collide with this guy. This guy might collide with this guy. But no, this guy could never, never, never collide with this guy over here. He just couldn't. So another way to say it is this way. All the slots on a hub are in the same collision domains. And all the slots on a hub could have collisions. But on a switch, every port on a switch is a separate collision domain, or another way to say it, switches separate collision domains. One more time. Every port on a switch is a separate collision domains, and switches separate collision domains. That's very important. Hubs don't, switches do. And the only way you're going to know this is you know what a hub or switch is from chapter 1 and 2, hopefully. I think I'm going to stop in a minute or two. Let me just say where I'm going. One more thing and then we'll stop, because I want to be able to review this stuff next week. All this is on a test, and I want you to see it twice. Next slide, and we'll stop it. Know about collision domains and the separating collision domain. So one more time, hubs do not. They're all the same. Every port in a switch is a separate collision domains. Switches separate collision domains. Last slide, and we're going home, but this is very important. Forget the top part. It's a best effort delivery. That's interesting. Ethernet detects damaged frames and cyclic redundancy check. Now, let's begin. This is important. Talking mainly to people who are here for chapter 2. How do we change a packet to a frame? We frame the packet. What do? On the front end of the packet, we frame it with the to and from MAC address. Here's the drum roll, everybody. On the rear end of the packet, we frame it with what? With the error checking software. The error checking software that frames it on the rear end is called the CRC, the cyclical redundancy check. What does it do? It checks errors in the frames. Now, this is important. Here's my lecture. Grandma sent you all her she has a tea set, and Grandma sent you her tea set. When you got it, it all arrived and it's beautifully packed. You opened it up and there's so many cups and saucers. But the soup tureen is damaged. I'm sorry, the main part is damaged. So you've got Grandma's tea set. Did you get it? Yes. Did you get it intact? Well, almost. Most parts are okay, but the soup tureen or one cup was damaged. You got a damaged packet. Did you get her tea set? Yes. Did you get it intact? No, you got it damaged. So what we're doing is we're detecting a damaged frame. We're detecting a frame where 1 was a 0 or a 0 was a 1. What you got was not the frame it said. Big cuidado. It does not detect a lost frame. Let me explain that. If Grandma's tea set was damaged, but it also got lost, you'd never know it was damaged because you'd never get a copy of it to see that the soup tureen was damaged. You would know it. So yes, they damaged it. They also lost it, and you never found out. It detects a damaged frame. It does not detect a lost frame. And where do you find it? You find it in the rear end of the frame. That is, you frame the packet by putting a MAC address in front. What did you put in the back? Some error checking. What do you call that error checking? You call that error checking the cyclical redundancy check. What is it? A thing that detects a damaged frame and is in the rear end of the frame to detect error checking. Is it in the packet? No, because you didn't put it in yet. Peter Piper picked a peck of pickled peppers. Now, I have a lot more to do, but I'm just getting worn out. I think you are. So I'm going to stop sharing. I think we're done. That Sean guy, you might want to talk, and Edward Gomez, you might want to talk to me too. Some people showed up late, and I'm hoping you know all the stuff from chapter 1 and 2. Just quick hint, your test is not next week. I think it's the week after. There'll be a review next week for, I believe, a test the week after. So if anybody has a question, you can ask it. If you want to go home, you can go home. I always do. I'm going to stick around for 5 or 10 minutes. We're going to finish this chapter on Wednesday. I'm going to finish it right to the end, including repeating the hard stuff. Repeat the CSMA CD, repeat the signal redundancy check, and then we'll finish it. And then we're done with this chapter. And next week we do chapter 4. Questions, comments? You want to throw a tomato? You can go home if you want to. The people who are new might want to stop and talk to me. I'm done.
Have a nice day, Professor.
Have a nice time. Okay. Now, who do I want to talk to? Sean Roche, have you ever been here before? Oh, yeah, you